Okay, so again, we have Xander, who is going to talk about applications of Riemann. And here we go.
Thanks a lot, DJ. So on Wednesday, well, my goal for today is to talk about a couple of different applications, but the first thing I'm going to do is go through and just review what we talked about on Wednesday, which was about the relationship between divisors and maps to projective space and the Riemann theorem itself. So for the moment, let's let C be a smooth projective curve. And we could loosen these things if we want to, but we won't need to for any of our applications, so we're not going to. The main thing that we spent most of our time on Wednesday talking about is that there is kind of a correspondence. It's not quite a bijection, at least not the way we stated it, but between divisors D on a curve. I'll put a little tilde over here to emphasize that this map is not really bijective. There are a lot of extra words we would have to add to make it a bijection, but and then on the other hand we have maps from C to a projective space. So on the one hand, the way this worked was that if we had a divisor D, we could send it to, we might, well actually first I should write down, I'll write it over here. Just to remind you what this vector space L of D is, we defined it to be the space of all functions f, that's rational functions on our curve, such that if D looks like this, minus, let's say, sum of MQ, Q, where the MPs and the NPs and MQs are all non-negative, so we're splitting it into two parts, then we want to require F has a pole of order at most, am I looking at the N's or the M's? Or, yeah, at most NP at P, and F has a 0 of order at least MQ at Q. And it's pretty easy to see that these form a vector space over the complex numbers. So when we have big positive integers, we are allowing poles, we're allowing more functions to be in our vector space. When we have very big negative integers in our coefficients, we're adding a bunch of conditions and making our vector space smaller. So we should expect, and the Riemann theorem tells us exactly how this happens, but we should expect that as the sum of all the NP minus the sum of all the NQ, as this gets really big, so should the dimension of that vector space. But so let's choose a basis, not for D, but for L of D, and then our map is going to send a point P on the curve to we just take each of these rational functions and evaluate them at P. And again, some of these things could blow up, so this won't be defined at every point of P. They could all be 0 simultaneously. This is one of the things where if I really wanted to have a bijection between these two things, I would need to add a lot more words, but we're going to brush that under the rug for now, and it won't come up in our applications. And then in the other direction, suppose we have a map from C to PR. We talked about how we can take the hyperplane at infinity in PR and intersect it with C to get a divisor C equal to, whoops, sorry, just C intersected with the hyperplane at infinity in this projective space. Gives us a divisor, and it turns out that these two things are actually usually inverse to each other. And we'll denote this map by phi sub b for the rest of today. So this is what we talked about, and so we can see that it would be really nice to understand the dimension of these vector spaces, because that tells us about where exactly all the maps to projective spaces from C land. It tells us which projective spaces we can get into, because this R is going to be equal to, I'll define little d to be the dimension of big D. So big D is a vector space, sorry, big L of D is a vector space, little l of D is just going to be an integer. And this R that our map lands into is L of D minus 1, since in here we have the, I guess technically I should have put zeros here, else that should already be an R minus 1, but the dimension of this projective space is related to the dimension of this vector space because of the fact that we're taking a basis for it and spreading it out into our coordinates. And the Riemann-Roch theorem tells us, put it right here. So for this part, we could relax the smooth and projective hypotheses. For this theorem, we cannot. So this is the Riemann-Roch theorem for curves, and it says there exists a non-negative integer g, which depends only on c, depending on c, such that when the degree of d is strictly bigger than 2g minus 2, L of d is equal to the degree plus 1 minus g. So what this tells us is that for divisors of big degree, whenever we add one extra condition to our divisor, we lose exactly one function. And whenever we allow one extra pole, we gain exactly one function. That degree, this part over here is just a constant. It's an important constant, but it's still just a constant. So as long as the degree stays bigger than this, when we wiggle the degree, the dimension of this vector space wiggles by exactly the same amount. So I'm going to do one quick sort of warm-up application, and then the rest of today I'm going to spend talking about how we can use this to understand Weierstrass points and automorphisms of curves. But for right now, I have a corollary of this, which says that if I pick any finite set of points in a curve, and this is still a smooth projective curve just like before, then C prime, which I'm defining to be C minus this finite set, is actually affine. So just to recall, what it means to be affine is that this thing is actually isomorphic, and I haven't really said what isomorphic means, but basically there's a polynomial map from here to some AR, so that the image, first of all, it'll be bijective, and we actually have something slightly stronger than that, but at the very least it'll be bijective, and the image is exactly cut out by some set of polynomials. So, for instance, A1 minus 0 as a subset of A1, this turns out to actually be affine, but the way it's embedded in A1 right now, that's not obvious. And if I looked at A2 minus 0 contained in A2, this thing is actually not affine, even though it lives inside of an affine subset. So when I say that this is affine, I actually mean that it's cut out by some polynomials all the way. Okay, so where does this statement come from? It comes from the following fact, which I'm not going to prove. but it says this. If D is a divisor on our curve C, such that whenever I take 2 points P and Q, they could be the same. This includes the case where P equals Q. Subtract them both off of D, I lose exactly 2 functions. This is our hypothesis. If we have a divisor so that subtracting off any 2 points causes us to lose exactly 2 functions in our vector space, then phi b, the map corresponding to this divisor, which goes from C to P, technically PLD minus 1, this is an embedding. So the way we should think about this proposition is that in the case where P and Q are 2 distinct points, losing 2 functions when you subtract them off turns out to be the same as saying that this map sends them to different points. So if we only have the case where P and Q are distinct, this is telling us that a weaker theorem would tell us that this map is injective. When the 2 points are equal, when P is equal to Q, LD minus 2P equal to LD minus 2, this turns out to imply that the map on tangent spaces at that point is injective. And then, furthermore, it turns out that when you have those 2 conditions, the map from the curve to projective space is actually an embedding. But you should think of the case when P and Q are equal and the case when P and Q are distinct as being 2 very different situations. One is telling you about the map being injective, and one is telling you about what it does locally. And those 2 conditions together give us an embedding.
How will taking 2 points out affect the genus of a curve?
Taking 2 points out. So the genus is only defined for projective curves.
Oh, so when you take 2 points out, you can't. So you can't.
You
can't somehow use Riemann-Roch to get an actual kind of understanding of when that drops by 2, right? Because
so keep in mind, we're not deleting these points from the curve.
no,
We're replacing the divisor
yeah.
D with D minus those 2 points.
Good point.
Yeah. But so, I mean, it is common to define the genus for curves that are not projective. And when you do this, you take your not projective curve and you sort of take a completion. You stick it into, you show that it's always going to be some projective curve minus a finite number of points. And you just define its genus to be the same as that. So if we took that definition, then the answer to your first question would be it never changes the genus just by definition.
But then Riemann-Roch here does give us a way to say, like, what we need P and Q to do to the degree of D, right?
Yes, exactly. And we're going to combine these 2 facts. So when we put Riemann-Roch together with this proposition, what we see is that if the degree of D is bigger than 2G, then you always have an embedding. Because whenever you subtract 2 points, it's still bigger than 2G minus 2. And we know that in that whole range, the degree and the dimension of this vector space vary together. So subtracting off 2 points is always going to kill our vector space by 2, as long as we're bigger, not than 2G minus 2, but now we have to go all the way up to 2G. Because to get this equation, we have to go down 2 steps. So let's see, what should I erase? I'll erase this explanation of the, you know what, here, I'll erase this definition of LD. I think that's probably the least important thing on the board at the moment. So the way we prove this corollary then is define D to be the sum of our finite set of points. So this is a divisor on C, and then set D prime to be 2G times 2, or 2G times D. We could take any big multiple. Anything bigger than 2G will work just fine also. And if we have lots of points, then we could choose something smaller than 2G. But we just need a divisor that's, its non-zero coefficients are only at these points, and it has degree bigger than 2g. So now, phi b prime gives us a map from C into some big projective space, we don't care which one. By the theorem, it's actually an embedding. And by what we have written down over here, because of the fact that these two maps are bijective, we actually know that when we intersect with the hyperplane at infinity, we get exactly the divisor that we started with. We get d prime. But for our purposes, we don't care about the multiplicities. All we care about is the set of points. Technically, I should write not C, but its image in this projective space. So now the thing about projective spaces is that we talked about this last time, how you can break them into two parts. You have the hyperplane at infinity, and then everything inside of that is an affine space. So this, or rather the complement of this, which is the image of C minus the hyperplane at infinity, this is exactly equal to C minus our finite set of points. But the way this all works out, we have this is equal to phi b prime of C intersect that affine space. So basically we found it, we wanted to get rid of some points, so we found an embedding that put those points at infinity, and then when we cut them out, we're left with something that's actually a curve in affine space. And that's the proof of the corollary.
So we get this condition of little l d minus p minus q equals l d minus 2 from Riemann-Roch because it scales like linearly with the degree.
Exactly, yeah. That's why we put a 2g here. We could, like I said, we could have put anything bigger. We just need something big enough that when we subtract off 2 points, we're still in the range where Riemann-Roch applies. Okay. So the next thing that I want to talk about kind of has to do with what happens when we're below this range. What happens when our divisors have small degree? And in general, it can be pretty complicated, but we're going to talk about one particular fairly simple class of divisors. So we're going to fix a point P on our curve and study the divisors n times that point. And actually, we'll only look at it for n non-negative. So there are a few things that we know about this right away. First of all, this, I'm not sure if I said this earlier, but on any projective curve, the only functions that are defined everywhere, that don't have any poles at all, are constants. So in particular, the Riemann-Roch space of 0 as a divisor is just going to be the complex numbers. So L of 0, little l of 0 is equal to 1. The other thing we know, thanks to Riemann-Roch, is that when n is bigger than 2g minus 2, little l of n times p is exactly what the Riemann-Roch theorem tells us, which is n plus 1 minus g. So the question is, what happens in this range from 0 to 2g minus 2? There are a couple things that we can say about this right away, and a couple things that will take a little bit more thought. So, first thing is, these integers are increasing. L of np, oops, fact, the Riemann-Roch space of LP is really just a subset of the next one. So this consists of all rational functions that blow up to order at most n. This consists of the ones that blow up to order at most n plus 1. So certainly all of these live in there. So we have a sequence of integers. These, I'll denote them by E, n, comma, p as a shorthand for this. And they start at 1 by 2g minus 2. So actually when n is equal to 2g minus 2, we have, or rather I should say 2g minus 1, because that's where this condition starts to kick in. This is going to be equal to g exactly. So over the course of 2g minus 2 steps, we go from 1 to g. So we're going to step up by exactly g minus 1. And what we're going to see in just a moment is that we can jump, the dimension of this vector space can jump by at most 1 at every step, which means that it jumps exactly half the time. So that's the last thing that we know about this, which is that, I guess I should use my new notation. E at n plus 1 minus E at n, it's certainly non-negative by this, and it's also less than or equal to 1. And the way we see this, we're going to look at a particular left exact sequence. So we have one part of it already. This injects into that, and then we have a map. So let's choose pi with a 0 of order 1 at p.
Could you just define a left exact sequence?
Okay, you know what, here, I won't talk about it that way. I'll just say the phrase left exact sequence is totally, it's not going to matter at all.
Okay.
Hopefully, what I'm talking about should become clear as I go through the construction anyways. So we're going to choose a function pi that has a 0 of order 1 at p, and this does always exist. It's important to keep in mind, though, that we don't care if pi has poles or zeros everywhere else. It's allowed to blow up or do whatever it wants out there. Now let's define a map from this vector space to the complex numbers. And we'll take a function, multiply it by pi to the n plus 1. So we've cleared out all of its poles. Now we definitely have something that's defined at p. So let's evaluate it there. So the main thing to note is that a function f here is going to map to 0 if and only if it doesn't blow up as much as it's allowed to. So the point is that if this thing still vanishes at p, then f must have had fewer poles than this thing had zeros. So in particular, this map, the kernel of this map, is exactly this subspace. So we get a map from the quotient to C. Now, this won't always be surjective. That's sort of the main point, is that this is not an isomorphism. Actually, because this is equal to the kernel and not just contained in it, we get an injection like that. So there are two cases. First of all, I'll call this quotient Q. We might have Q equal to 0. right? That's the case where everything in here maps to 0. No, sorry. Everything in here is actually in there. So this is equivalent to, for instance, saying that no function has a pole of order exactly n plus 1. These two vector spaces are equal, so there's nothing just in here that's not there. So everything gets cleared to 0 and we get zeros over there. The other case is that Q is actually equal to C. In this case, we see that the quotient has dimension 1, which means that we had a 1 over here. So these two cases that I'm writing down are the same as the cases here where we have a 0 or a 1. And in particular, we see that with the difference equal to 0, if and only if, or here, difference equal to 1 if and only if there exists a function with a pole of order n plus 1 and delta equal to 0 otherwise. Does that all make sense? Are there any questions about this?
So why is L0 one-dimensional?
L0 is one-dimensional, so this is something that I didn't prove. What I'm saying here is, so the elements of L0, this is the vector space of all functions that have no zeros and no poles. And it turns out that if we're on a projective curve, the only functions like that are constants. So this is a generalization of the fact that the only
Wait, why does it have no zeros?
Huh?
Can't it have...
Oh, it actually, you're right. It can have zeros, but it never will.
Okay.
This is sort of another, the number of zeros and the number of poles always add up. So if you had a 0, you would have to have a pole. But again, that fact is not something that I've proven, and it's definitely not something that's obvious. But
that needs irreducibility, probably. Or
yeah, I think you're right.
Okay.
Okay. So now I'm going to make... So using these 4 facts that I have written down, we see that out of the set of integers from 1 to 2g minus 2, exactly g minus 1 of them are going to be points where the size of this vector space jumps. So let's define the gap sequence at P to be, we'll denote it by GP, and it is we have the set of integers from 1 to 2g minus 2, and this is the subset of them, such that no function has a pole of exactly that order. So the first thing that's kind of a little bit interesting about these sets is that you might think, so if we take the gap sequence for a particular point and just add up all the values, I guess technically I should write the sum of k over all k in the gap sequence. You might think the smallest sum you can possibly get is when you have the numbers 1 from 1 to g minus 1. No, sorry, that's actually true. You might think the largest sum you can possibly get is when you have the numbers from g to 2g to 2g minus 2, the largest numbers you could possibly get. But it turns out that that sequence can never, ever happen. And it's pretty easy to see this. So actually, we have the following fact, which is that the largest sum of gap values we can have is g squared, which happens exactly when the gap sequence is the set of all odd integers in that range. The reason for this is that if I have, for instance, let's say a function that blows up to order 2 and a function that blows up to order 3, and I multiply them together, I get a function that blows up to order 5. If I have, so a similar argument shows that if 1 is not in the gap sequence, we have an issue. If there's a function that blows up to order exactly 1, then there's a function that blows up to order 2 and 3 and 4 and 5 just by taking its powers. And in particular, if 1 is not in the gap sequence, then the gap sequence is empty. But that definitely can't happen, because we know that there are always exactly g minus 1 numbers in here. So this is the case where there's a function that blows up to order 2. And as a result, there's also one that blows up to order 4 and 6 and 8. We have all the even values, and so all the odd values have to be in the gap sequence, because there are only g minus 1 of them left over. So this is the largest one we can possibly get. The smallest, however, is exactly the one that you would think. It's 1/2 g times g minus 1, and that happens exactly when gp is equal to just the first g minus 1 integers, from 1 to g minus 1. So this leads us to the main definition that I want to talk about, which is P is a Weierstrass point if its gap sequence is not the smallest possible one. So when we have the smallest possible gap sequence, that means as we take the multiples of our point, this point is putting off gaining functions for as long as it possibly can. So eventually, by the time we get to 2g minus 2, there have to be g functions there. It's going to wait until g minus 1 to get any at all. It's going to wait as long as it's possibly allowed to. All the other points, all the points that pick up functions before they're required to, those are called Weierstrass points. And in fact, there are only finitely many of them on a curve. So this is a really surprising fact, that on any smooth projective curve, almost every point puts off gaining rational functions for as long as it's allowed to. And there's only a finite collection of points that don't do this. And in fact, we can get something a little bit better than there are only finitely many. We can get something of a count. So if we define W of P, this is called the Weierstrass weight, to be the sum of the gap sequence minus, we're just going to subtract off the smallest sum that this could possibly be. So now, this is 0 if and only if we have, this is 0 when we don't have a Weierstrass point, and non-zero at the finitely many Weierstrass points. And the theorem says that if we add these up for all points in our curve, and we can do that since only a few of them are non-zero, we get g minus 1 times g plus 1. And if you went through and counted this all up, you would find the following thing, which is that every curve has at least 2g plus 2 Weierstrass points with equality if and only if every one of them has the biggest gap sequence possible. So the gap sequence consisting of all odd integers in that range. So what we're saying here is just that 2g plus 2 times g squared is exactly this value. So if you have any point that is not of this form, you'll have a sum of gap values. You'll have a Weierstrass weight that's smaller than the largest one it's allowed to have. So you need to have extra Weierstrass points to make up for that difference. And then you'll have strictly more than 2g plus 2 of them.
Wait, that multiplication seems off by like a factor of 2
Let's see.
or something.
So this is g cubed minus g. I don't know, we can go through and check these numbers. The specific numbers won't exactly matter for what we're about to do.
Sure.
It's totally possible that I wrote something down wrong, but we can check them later just to be sure. Okay, so the last thing I want to do is use this theorem about the number of Weierstrass points to prove the following thing. And actually, I won't quite prove it all the way. If the genus of C is bigger than 2, then C has only finitely many automorphisms. In fact, if you're interested, the number of automorphisms is less than or equal to 84 times g minus 1. Getting the specific, it's a very strange theorem, but getting this specific bound is a little bit tougher than actually just proving that they're finite. And another thing is that the finiteness fact holds over any field. Any field at all, whether it's algebraically closed or you don't need any conditions at all to know that curves of genus at least 2 have only finitely many automorphisms. This specific bound actually fails unless, I think the broadest circumstances you can prove it is for a perfect field of characteristic 0. So in particular, over the complex numbers, which is what we're doing, we do have this specific bound, but I'm not going to prove it. And it doesn't hold in general. Everything I've said about Weierstrass points does hold completely generally, though. So, actually, we need one lemma first. A lemma that I'm not going to prove, but it doesn't use much machinery, it's just kind of a clever argument. If we have any automorphism of a curve that's not the identity, then it has at most 2g plus 2 fixed points. So this is lining up pretty nicely. The numbers are exactly kind of where we want them to be. And the proof, we'll do it in 2 cases, and I'm actually not going to do one of the cases. It would take a little bit too much time, but first of all...
Sorry, did you say phi is an automorphism, or...?
Phi is an automorphism. Here, I'll put a little equal sign over it. So this is an isomorphism of C with itself, and it's not the identity. Obviously, the identity is going to have infinitely many fixed points. But, so there's one case, is if the number of Weierstrass points is bigger than 2g plus 2, every automorphism has to permute them. So this is maybe not totally obvious from the way I've discussed them, but the Weierstrass points are an isomorphism invariant. This is something that's intrinsic to the structure of the curve. It doesn't matter where we put it or how it embeds it. This is part of the structure of the curve, and so every automorphism has to take every Weierstrass point to another Weierstrass point. So in particular, we have a map from the automorphism group of C to the symmetric group on whatever the number of Weierstrass points is. And it takes phi to whatever, oh, so this, by the way, is the proof of the theorem, not of the lemma, in case that wasn't clear. So to whatever permutation it induces on the Weierstrass points. And in fact, this map is injective because of the lemma. Any automorphism that fixes, so an automorphism that's in the kernel of this map is one that induces a trivial permutation. So it fixes every Weierstrass point. But there are more than 2G plus 2 of them. So that means that it has to be 0. So we actually have an injection from the automorphisms of C into a finite group. So we're done in this case. The other case, which is a little bit trickier, is when it's actually equal to 2G plus 2. In that case, we still get the same map, but it's not injective. We're able to show that the kernel is exactly a copy of Z mod 2 that lives inside of this automorphism group. And that's the last thing that I want to talk about for the last couple minutes that I have here is what I like to think of as a classification theorem for curves. And this is going to tell us a little bit about where that copy of Z mod 2 comes from, although I still won't prove that theorem completely. So the first thing that I'm going to say is, I'll call it a definition proposition. The following two things are equivalent. One is that there are more than 2G plus 2 Weierstrass points. So there are lots of Weierstrass points. The other condition, and this is sort of a very surprising equivalence, but if you remember a while ago on Wednesday when I first stated the Riemann-Roch theorem, I gave you a second form that had a divisor that I denoted by k in it, which had degree 2G minus 2, and it was called the canonical divisor. And I never really explained where that came from, and I still won't. But this condition of having more than 2G plus 2 Weierstrass points is equivalent to saying that the map that we get from the canonical divisor is an embedding. And in this case, we call C a canonical curve. So this is, the really nice thing about canonical curves is that if you have two of them living anywhere and you want to tell whether they're isomorphic, first of all, check if they have the same genus. If they don't, then they're definitely not isomorphic. The next thing you do is that should be PR. So if they have the same genus, then these embedded images are going to live in the same projective space. So you can embed them. And now all you have to do is look at their images and ask, are they actually set theoretically equal up to maybe a linear change of variables? That's the worst thing that you need to worry about for checking whether two canonical curves are isomorphic is a linear change of variables on projective space. So that seems like a really, really nice condition. And the surprising thing is that its negation is also a very, very nice condition. So this is one of the best things, in my opinion, about the theory of algebraic curves, is that we can classify them into two groups, one of which has a really nice property that makes them easy to understand. And somehow, its complement also has a really nice property that makes them easy to understand. So the last fact that I'm going to write down is that this will be another, the following are equivalent. Whoops, start at 1. C is not canonical. And I could write down about a dozen other equivalences here, but I'm only going to put, I think, 2 more. Let's see, what did I have written down? Well, this one I guess is kind of obvious because I already said these 2 things are equivalent, but C has 2G plus 2 Weierstrass points. And finally, this is a word that I used a few times over the first couple lectures. C is hyperelliptic. So what I told you guys that hyperelliptic means before is that C actually lives in the projective plane, and we get it somehow by taking the square root of a polynomial in just one of our coordinates. So it'll always be symmetric across the y-axis, and it'll look something like this. And those 2G plus 2 Weierstrass points are exactly these guys. And then, if there is one, the point of infinity. Of course, it's also possible our whole curve could just be made up of bulbs like this, in which case, these are the Weierstrass points. But in general, this is what every curve that is not canonical looks like. And now you can see this copy of Z mod 2 inside the automorphism group. It's, when I draw it this way, it's the obvious symmetry that just reflects across the y-axis. It definitely fixes all of the Weierstrass points, and it's not too difficult to show that this is, because the Weierstrass points all lie along the y-axis, and it's not too difficult to show that this is the only automorphism that can do that, is this one that reflects. If you compose it with itself, it's 0, so it generates a cyclic group of order 2, and then we see that that is a copy of Z mod 2 inside the automorphism group, and it's precisely the kernel of that map to the symmetric group. So we have this map mapping to a finite group with a finite kernel, which means that this thing has to be finite. And that's all I have to say. Thank you very much. Are there any questions?
Is there a nice way to tell when hyperelliptic curves are isomorphic?
I'm sure there is, because they do have a very simple structure, although I don't know. I certainly can't think of an algorithm off the top of my head like I can for something like canonical curves, which are a lot simpler. I can't imagine it's very difficult though, but yeah, it's not quite obvious to me.
If someone wanted to read more about this, where might they read it?
Let's see. Fulton's Algebraic Curves is a good book. I haven't looked at it very much, but the little that I've seen is very good. There's a book called, where I learned most of the stuff that I was talking about today with Weierstrass points, is from a book called Geometry of Algebraic Curves. It's commonly just called ACGH. You'll hear people refer to it as that for, I think that's Arborello, Cornalba, I hope I'm getting these right, and then Griffiths and Harris. That's a really great book. I'm a big fan of Ravi Vakil's notes. He has a couple chapters on curves, although the way he sets it up as applications of some really big machinery. So sort of to read his chapter on curves, you need to read a lot. You need to read a lot of the rest of them, whereas these are books specifically on curves where you can jump in and start learning about these specific problems without learning all of algebraic geometry first.
Any other questions? Well then, let's thank our speaker again.